Welcome to this explainer. Today, we're decoding the exact hardware clock numbers you absolutely need to understand to optimize your machine learning pipelines. Because whether you're training massive models or getting down in the weeds writing custom CUDA kernels, really understanding your hardware specs is the foundation of getting good performance. So let's start with a mystery that honestly plagues a lot of us when we first start out. You look at your system, right, and you see a 4 GHz CPU sitting right next to a 2 GHz GPU. It literally has half the clock speed. Yet somehow your large model trains orders of magnitude faster on that 2 GHz GPU. Why? What is actually happening under the hood there? Well, to solve this, we kind of need to define what a clock actually is in machine learning terms. It's really just a repeating tick. The clock speed, which you see as megahertz or gigahertz, is simply how many of those ticks happen every single second. And each tick allows the hardware to advance exactly one step in its pipeline, whether that's executing some arithmetic, loading a memory block, or just shuffling data around. It helps to think of your hardware like a giant factory. Your total machine learning throughput actually requires multiplying three things together. Step 1, the clock speed, so how fast the workers take a step. Step 2, the work done per cycle, like how many floating point operations happen per tick. And steps 3, the total number of parallel units, or workers, you have running on the floor. So let me ask you this. If you've got GPU A running at 2 GHz and GPU B running at 2.4 GHz on the exact same architecture, can you guarantee B is faster? Absolutely not. No way. This formula reveals exactly why higher gigahertz alone doesn't guarantee speed. Things like memory bandwidth, the number of tensor cores, power limits, and honestly, the specific type of workload you're running. They matter just as much as that raw clock speed. All right, let's look at CPU and RAM pipelines. This is all about feeding the beast. Before we even touch the GPU, we have to understand how the data gets there. So on the CPU side of your rig, the CPU core clock dictates how fast each core runs its instruction pipeline. For ML specifically, this directly impacts how fast your data loaders can actually perform data loading, tokenization, preprocessing, and augmentation. If you're running a single-threaded or even lightly threaded data loader, a higher CPU core clock gives you much faster per-sample preprocessing, which keeps your whole pipeline moving. Meanwhile, your system RAM has its own clock. You usually see this represented by DDR ratings, like 3200 megahertz, which, fun fact, are actually data rates, not raw frequencies. But this clock dictates the memory bandwidth that is so crucial for feeding massive batches to the CPU and eventually sending them over the PCIe bus to the GPU. If you're dealing with enormous data sets or running a multi-GPU setup, a higher RAM clock is a total lifesaver. Moving on to the next part. Inside the GPU, the actual ML workhorse. Let's push our data over that PCIe bus and explore the critical clock domains inside the GPU itself. First up, we've got the GPU core, or SM clock. You'll often see this called the GPU clock or shader clock on spec sheets. This determines exactly how fast your tensor cores, your FP32 and FP64 units, and your warp schedulers are actually running. A higher GPU core clock means more matrix multiplications and convolutions per second. If your workload is compute-bound, this number is absolutely vital. On the flip side, we have the VRAM clock. This is the clock for the GDDR or HBM memory chips physically sitting on the GPU. It dictates how fast data, specifically your weights, your gradients, and your activations, moves between the VRAM itself and the streaming multiprocessors. If you're training large transformers or cranking up your batch sizes, this memory bandwidth usually becomes your primary bottleneck. Your model becomes memory-bound. Oh, and as a quick aside, there is technically a third clock. The video or display engine clock. This drives display outputs and video encode/decode operations. Honestly, for standard machine learning training, this is almost entirely irrelevant. You can basically ignore it unless your pipeline heavily relies on real-time video frame decoding, like in some streaming computer vision tasks. Okay, here is the hardware disambiguation guide. Let's synthesize all these moving parts so you're never confused by a spec sheet again. If you look at this, notice how perfectly these components divide the labor. The CPU core and system RAM, they handle data preparation and feeding. Inside the GPU, the compute cores and SM clock drive the heavy mathematical lifting, all those matrix ops. Meanwhile, the GPU VRAM clock dictates the data transfer speed. When you're reading specs, you've got to map the numbers directly to whatever the bottleneck is for your specific workload. And really, this brings us right back to our opening mystery. Comparing CPU and GPU gigahertz is completely useless because architecturally, they are wildly different. CPUs use a few really complex cores designed for sequential, heavy logic tasks. GPUs, they leverage thousands of simpler workers designed for massive parallelism. So yeah, a 2 GHz GPU doing thousands of operations per tick is going to absolutely obliterate a 4 GHz CPU doing only a few. All right, let's talk about optimizing real ML scenarios. How does all this theoretical knowledge actually change the way we configure our workflows? When you're training large language models or massive transformers, you're basically fighting a war on two fronts. You absolutely need high GPU core clocks to handle the incredibly compute-heavy general matrix multiplications, or GEMs, but at the exact same time, you are equally reliant on VRAM bandwidth, governed by that VRAM clock, to constantly shuffle massive weights and gradients back and forth. Now, for inference at scale, those bottlenecks kind of shift dynamically. Batched requests can easily hit compute bottlenecks if the operations per sample are really high, meaning that GPU core clock really matters. But if you're running massive models with a ton of concurrent requests, you'll probably hit a memory bandwidth bottleneck first. Or if you're doing single-sample low-latency inference, that relies heavily on rapid VRAM fetch speeds to instantly pull the required weights. And if you're down in the trenches writing custom CUDA kernels, you can literally use this directly. Bumping up the GPU core clock, maybe by adjusting your power limits, will drastically speed up arithmetic-heavy operations like convolutions. On the other hand, if your kernel is relying on heavy load and store operations, sparse operations, or large tiling, you actually need to increase the VRAM clock or just switch to a GPU with better memory bandwidth. Okay, let's wrap this up. Recap. Master your hardware specs. Let's lock in the key takeaways. Here are the 4 big things you need to remember. 1. Throughput is always a formula of clock speed, work per cycle, and parallel units. 2. The GPU core clock handles your math speed. 3. The VRAM clock handles your data bandwidths. And 4, the most important one, whenever you are optimizing, your very first step must be identifying whether your workload is compute-bound or memory-bound. Match your hardware to your specific bottleneck. Which brings us to the ultimate question for you. Don't just take my word for it. I challenge you, right now, open your terminal, fire up NVIDIA Insight, or just run NVIDIA-SMI. Look at the model you're running. Look at your core clock and your memory clock. Is your workload compute-bound, waiting on the math, or is it memory-bound, waiting on the data? Because once you figure that out, you know exactly how to speed it up. Happy optimizing!